Hi, welcome to my 166th video on problem solving for financial math actuarial exam 2, and I'm trying something new here. As you can see, I'm trying to record myself, show my face as I record my screen at the same time. I've never tried this before, so I'm not exactly sure how it's going to look or go, but I'm doing my best and enjoying some of the background here. You can see I've got an Einstein up here somewhere. I'm not exactly sure where my finger's pointing because I can't actually see myself on the screen. And, well, if you happen to be a Pepsi executive, I've got a product placement here. You can see I've got a Pepsi can. So, you can send me my $1,000 check in the mail to Bethel University, okay? Just joking. Anyway, I've been pretty busy here recently with, of course, Christmas time holidays and so forth. And also here at the beginning of 2019, I've been busy starting my very first blog. It's called infinityisreallybig.com, and I hope you take the time to visit it. I'll show you a little bit about it. I'll do a more general announcement for my wider YouTube audience here soon. But here, you that have been following the financial math videos, you get the first look at it. Here's what it looks like. You can see it's kind of a pretty picture in the back. Infinity is really big. Bill Kinney's blog on mathematics, applications, life, and Christian faith. So I'm going to be sharing about myself in addition to the math, about my faith, and trying to give encouragement to people. Mostly it's going to be about math and its applications, but every once in a while I'll share about my life and my faith. And so far I don't have a ton of posts, though the posts that I do have on there are pretty long. I didn't want them to be quite so long, but that's the way they are. I think in general in the future the posts will be shorter, so don't let the length of these posts scare you off. You can see I've got one here about deconstructing the mean value theorem, part 2. There's a part 1 that I did, I think, last week sometime. I've got also some posts about financial math. This post from January 11th is actually fairly simple, the basics of financial math. The other stuff that I did here in this post, Financial Math Tools, Substitution, Quadratic Formula, Logarithms, and Functional Thinking, is a bit more complicated, a bit more advanced. Here's more about the mean value theorem, more about financial math, and I have my initial post being back on January 3rd called The Road Ahead. And I am trying to make these somewhat related to Mathematica, though it's not as ideal as I was hoping. I was hoping I could make Mathematica CDFs, computable document formats that can be put into the websites themselves, but it looks like at the moment that's not really so compatible with most browsers. And so the animations that I make that do come from Mathematica are really just, well, animated GIFs in this case. So it goes back and forth. You can see the animation. I do show the Mathematica code in some of these posts. I think in this one I did not here. But it will give you a visual sense of what's going on. So there's that intuition that I think is important with problem solving. But there's a lot of detail here, a lot of math detail. You know, the initial parts of these posts will be more understandable than the later parts. Usually these posts get harder as you go, but you know, depending on the kind of endurance you have to try to understand this kind of stuff will determine how far you get in each post. But I hope you find something valuable out of them. All right, this was actually a post that I did just earlier today, here, January 15th, 2019. All right, but for this video, the rest of this video, we're going to go back to financial math. And the rest of it's actually not too hard here. We're doing start problem 7.1.10 in Broverman, and it's actually, relatively speaking, compared to some of the videos we've been doing recently, it's fairly easy. The problem statement is to verify algebraically that the Macaulay duration of a coupon bond is a decreasing function of the coupon rate. The Macaulay duration of a coupon bond is a decreasing function of the coupon rate. All right, it's not as hard as it sounds, though the calculations are a little tricky. But based on things we've done recently, it's definitely not quite as hard as that. So use your imagination here. We've got a coupon bond with n coupons paid. You know, oftentimes it would be every half year. Periodic yield rate, if the coupons are paid every half year, this yield rate would be a semi-annual yield rate. Periodic discount factor, V is 1 plus I to the negative 1, and periodic coupon rate of R. Not saying what the face value is because we've seen that the face value cancels out in the numerator and denominator in the formula for the Macaulay duration, this formula right here. The KT would involve F times R. but it's in the top and the bottom, so the f can be factored out and canceled out. This is the definition of the Macaulay duration. And if it's a coupon bond, we have also seen previously in other videos that you can expand the Macaulay duration in this way. Now, if you haven't seen this before, you can certainly think about it. In the numerator, we have a weighted average of the payments. The KTs represent the payments. We've got 1 plus I to the negative t power, so these are v to the t power. Excuse me while I move around a little bit here to get more comfortable. You multiply those by the time of payment, t, and you add those up. So the t's that are the times of payments are the one that you don't actually see in front of this term, then a 2, then a 3, then a 4, etc. through an n minus 1. You also have the coupons themselves, the r's. Again, the f got canceled out. In the last term, when t is n, you've got an n here. You also have a 1 plus r times 1 plus I to the negative n. The 1, the r comes from the coupon payment, the very last coupon payment, and the 1 comes from the redemption amount, which is the same as the face value. And again, these are all being discounted back to time 0. In the denominator of the fraction, you do not multiply by t, so you don't see the 1, the 2, the 3, the 4. It's just a bunch of 1s multiplied by the r's here. Based on formulas for both ordinary annuity immediates and increasing annuities, you can write the top involving IAN and the bottom involving just AN. And that's one way you can write the formula for the Macaulay duration of a coupon bond like this. We can enter this formula into Mathematica as a function, I and R being sort of the main variables of the function, and N being sort of a parameter that we can change representing the number of coupons. And we can first visualize the fact that we are trying to verify here that the Macaulay duration of a coupon bond is a decreasing function of the coupon rate. So we should see a graph that decreases as R increases. I've made a multivariable graph here. This is in Mathematica. This is with plot 3D. We're graphing the Macaulay duration as a function of I and R. I is going to be pointing to the right in the picture, and R is going to be kind of going into the screen. And it's a little hard to see here when n is small, but if we increase n, we see a little bit more clearly, once it finishes rendering, that you've got a decreasing function of r. For any fixed value of I, think about fixed lines going back and forth this way, this is a decreasing function of r. It's going down as we move to the right here, as r increases, going to the right here and kind of into the screen. This function goes down. It's a decreasing function of r. You also see this blue dot here. I put that there for just to remind you of something from videos 155 and 165. 165 being the very last one I did last month, December 2018. That actually, it's kind of funny, as the number of coupon payments goes up, the Macaulay duration, which is the output of this graph, the height of the graph, goes up initially. You see the blue dot going up initially, at least when n is small. Let me make n small again. Watch, the blue dot goes up initially, but then if n gets high enough, it can start to go back down again. We saw that when the coupon rate, R, is relatively small compared to the yield rate, I in this case, that can happen. That blue dot initially goes up at first as n increases, but then it goes back down. R is fairly small there for that blue dot compared to the value of I. So that's just to relate it to some previous videos that you've seen if you have been following along. Alright, now for the main content of this video. By the quotient rule, we can differentiate this Macaulay duration with respect to R. So we need to use its formula in this form. This is the best form to use it for. We don't want to use this form of it, okay? Use this form to take the derivative. We need the quotient rule because you see an R both in the numerator and denominator. So that's what's done here. We've got the low times the derivative of the high, which is this IAN, because the high is a linear, both the top and the bottom actually are linear functions of R. These derivatives, technically speaking, are fairly simple. If you differentiate the top here with respect to R, you're just going to get the coefficient of R. That's where this IAN comes from. Minus the top times the derivative of the bottom. This AN right here is the derivative of the bottom. There's the bottom right there as a function of R. It's a linear function. AN is the coefficient. That's what you see here. And then we've got the square of the bottom down here. Compare that with this right here. And we did use the quotient rule here. That's just a matter of simplification. You can multiply the IAN through the parentheses here. You can multiply the AN through the parentheses here. When you do that, you get this, and there is cancellation that goes on. This right here will cancel with this right here. So you can simplify it to this, and then you can factor a v to the n out of the top, and you can also bring the denominator of the fraction out in front like this, and you're left with this thing being multiplied by this thing. This thing right here is positive as long as your interest rate, as it always is bigger than -1. This thing will be positive, so v is positive. So the sign of this derivative is the same as the sign of this difference. That's what I say here. The sign of this derivative is the same as the sign of that difference right there. But it's relatively easy to determine the sign of this difference. By definition of IAN, your present value of an increasing annuity, and AN, your present value of an annuity immediate, a basic annuity immediate, using their formulas, you can write this difference in this way. And all these coefficients that you see here are negative. We are implicitly assuming that n is bigger than 1, then 2, then 3, etc. in this expression that we've written here. So these coefficients are all negative and v is positive. You definitely get a negative quantity here. That difference is negative, making the derivative with respect to r negative as well. So the Macaulay duration is a decreasing function of r for any fixed value of I. Thought it might be interesting to actually differentiate with respect to r using Mathematica. There's what you get. Then we could plot this derivative with respect to r in Mathematica as well, and see that as a function of r, it's negative. There's the derivative with respect to r. I guess I could have plotted it with respect to I as well, and it would still be negative. I could have made a three-dimensional plot. Another illustration of this fact here. Okay, so I hope you enjoyed that, and yeah, do go ahead and visit my blog, infinityisreallybig.com. I'm going to be trying to post quite a lot on both financial math and real analysis in the coming months, because those are my most popular YouTube topics, but I eventually want to do a lot of other topics: probability, statistics, calculus, more basic calculus than real analysis, differential equations, that kind of thing. So keep visiting the site, maybe become a subscriber, and hope you get a lot out of it. Thanks.